And those are the reasons for why One Direction and Travis Scott are legit the two worst artists of all time. Cool. So here is our problem that we left off with on Friday. And we're going to make a big follow-up statement here, followed by maybe a couple little nice reminders from math. The area under a velocity versus time graph. Now, I'm trying to be concise here, but just a heads up, when I talk about the area under, we're talking the area between the graph and the x-axis, because if you just let it go all the way underneath, then it's infinity area, and all of a sudden doesn't mean anything. The area under a velocity time graph is the what? Did we just find based on this problem that we worked last class? The displacement. Thank you, Tolly. Okay. We can get the displacement from these graphs. Now, beyond that, I'm not going to write it again because we've, I imagine, written it several times here. But what is the slope of that line? And maybe I will write it. The slope is what? And let's just think about what would happen here. Change in y would be a change in meters per second over, what's the change in time? So what's meters per second telling us? Boom, acceleration. Now the cool thing, I hope the cool thing, is that we have the opportunity then to think about these problems in terms of their graphs alone. If we were able to record data that was way too crazy to deal with mathematically, we could still do a lot of the math here without having to jump into calculus, assuming that the shapes aren't too crazy. All right. So last class we did these. I'm going to do a quick reminder with just some math stuff that if you need it, cool. If you don't, cool. But because we're going to be looking for areas, it might be worthwhile to have a few different formula just kind of at our disposal. So we'll have a quick recall. These are just area of basic polygons in case you need it. Area of, and we'll just say dot, 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 and we'll write a couple of them. Okay. We're not going to do anything crazy here. If you wanted the area of, I don't know, a rectangle. And this is silly, but my rectangle, the way that I shorthand it is like that. Rect with the angle sign from geometry. How do you find the area of a rectangle? It's either length times width or base times height, however you'd rather think of it. Same values, just assign B and H. Okay, give me another basic shape that we can deal with. A triangle. Man, I am just super forgetful. What's the area of a triangle? 1/2 base times height. Now, I have no issue writing it like this. You will, though, just a warning, you will see me do BH over 2 instead, just because I think it's cleaner to write. Any other basic shapes that you guys know of? And obviously you do, but I don't know if you're going to guess this one. What's a trapezoid? So I'm going to give you about 15 seconds with your neighbors. How do you describe trapezoid to me? Go. Just in case, a trapezoid, guys, you do not have to draw the shape, but it's this thing. Now, if it's an isosceles trapezoid, it's probably the one that you're thinking of, but they don't have to be isosceles. To make this a trapezoid, all we require is those marks indicating that what is true about those things. They're parallel. Now, there's a couple different ways that we can do this, and it's going to depend on the problem, because here in just a moment, we're going to see this happening. But the first way that I look at this is I would just cut this thing into two shapes that are easier to deal with. Do you agree that we could just look at this as the area of, I don't know, this triangle? Plus the area of that rectangle? Like, that would be a good way just to get it. It's not as, steadfast formula. But you could certainly just cut it up like that and do so. You could cut it in other ways, too. You could do it two triangles. It's entirely up to you what you do. All right, but there's a better formula. Now, for this, you may not recall it. You might. 1/2 height times the sum of the bases. B1 plus B2. where the bases are just the lengths of your parallel sides. So here's base 1 or 2, and then here's the other base up here. All right. Now, immediately we're going to use one or all of these in just a moment. If we look at the problems from Friday, and I'll give everybody a second to write that, we only did a couple different problems with acceleration, right? Maybe one like actual problem, then one graph problem, which I guess they're both really problems. But here's what I want us to think about. In this situation, we had a car that's slowing down and we had a velocity winding up at 0, right? And its initial velocity wasn't 0. And that's okay, we dealt with it mathematically. We are going to derive today a couple more equations to deal with that will help us solve like way more problems than we have the ability to right now. So to start off with this, I don't want to get like too super crazy with everything, but let's make sense of what's going on. I want us to consider another graph and another problem to help us get some equations. So I'm going to slide over just a skosh because it bugs me that that's there. And here we go. Today's main focus, our first main focus anyway, it's still within this whole equations idea. The larger overall topic is position with constant acceleration. So real quickly, what sort of acceleration are we working with? Constant. That is the most important part for right now. So what I want us to think about is, let's think about a velocity time graph. And you can just do v-t if you want to. But I want to think about velocity time graphs with non-zero initial velocity. Okay. Now, reminder, our acceleration is constant, which is going to make this as nice as possible. I'm going to give us a graph that we're going to use to think about with like real values and stuff. But when we actually work these things out, we are not going to use the values. They'll just be there to help us think about it, okay? Cool. So let's say we get a lovely velocity versus time graph. And everything is positive, which makes things nice. And I'll just say velocity in meters per second and time in seconds. And I'm only going to put two values on the y-axis. I'm going to put 5 and 10. And I know it looks like it should be all the way up, but it's going to bug me. So there's 5, and we'll say 10 is right there. Don't even need 15, but I have to include it. Now, beyond that, I'm also going to go all the way out here. Don't care about the scale. I'm just going to put 10. We see that on this graph, we're going to have 10 seconds of time at which we can look at. So here we go. Let's say that our graph is represented, and it's going to end at 10:10, just so you know. So I'll put, there's my final position, or my final ordered pair, rather. And then we're going to start here. Here's the graph of velocity versus time. Now, as we go through this, there's a couple different things that we can see. Maybe. We'll see if we can pick them out. First thing that I care about is whatever object we're looking at accelerating. How can you tell, Fern? Positive slope. Perfect. Or, if you don't want to have to think about the slope because maybe that's not your first thought, is my velocity changing? Does it, like, it goes from 5 to 10, right? Boom. We're accelerating. We have to be. There's no other option. Okay. Beyond that, I have all this information. If we have time, which we do, and we have velocity, which we do, we're going to be able to find, what do we say the area underneath this is going to be? One more time. Displacement. So check it out. We're going to make a big statement. If we have time and velocity, we can find, and rather than just saying displacement, which you're certainly right about that, Delilah, what if I say final position? Is that a part of my displacement? And I'll pause there because everybody's writing. If I wanted to find displacement, or delta x, it's just my final position minus my initial, right? So I'm arguing that we're going to try to find an object's final position, which is part of the displacement, so they're certainly related, but only using this information. Now, we're going to, I think, be able to recognize If I made this little shape, or this thing, into a full polygon, can you tell me what shape it is? Trapezoid. Now, we could use the trapezoid formula, but I also think maybe it's easier if we just split this guy into two different regions. If we see two different regions here, I'll have this region there, and I'll try to use a different color here, this beautiful region here. If I wanted the total area of this figure, what do you do with those two regions? You just add them up, right? So let's start thinking about this, and we'll, again, the numbers don't matter right now. I just want them to be able to think about it in a concrete sense. We're just going to work out the actual part, though. So let's just think this out. If I wanted to continue on, delta x contains x sub f. I think I know that delta x would be equal to the area of the rectangle plus the area of the triangle. Are you guys okay with that part? Now, I'm going to introduce some Greek letters just so we can practice with them. I'm going to say this region, we'll call it region alpha. It looks like a fish. Alpha looks like this if you want to draw it. This region up here, and I'm going to make that much more bold and showing up here, alpha. And this region is beta, which is a capital B with a tail. We'll make it a little bit nicer. B with a tail. We have two regions there, alpha and beta. Now, for either region that we're dealing with, do you guys need to see me draw the alpha again? Alpha and beta just has that tail. Cool. In either of these regions, if we were trying to find the area of it, it would be meters per second times seconds, right? And it would just be a displacement itself. So there's some amount of displacement represented by this bottom box, and there's another amount represented up here. I just want to break this apart as easily as we can. If we split it up, do you agree that this would be the displacement, too bold, the displacement delta x found in region alpha, plus the displacement delta x found in region beta? Yay, nay, just before we get too heavy, because the Greek stuff throws people off sometimes. Some indication. Thumbs up says I'm okay. Thumbs down says uh-uh. Okay. Now, let's start going a little bit further at this. How would you find the region alpha? What's the height of that rectangle? I'm sorry. And there's a bunch of different answers I'm expecting. Guarantee somebody's got 5. 5 is a good answer. What does 5 represent on this graph? Notice it's on the which axis? And y-axis measures my velocity, right? At which point in time is the velocity 5? At time 0. If only there were a better way to say the velocity at time 0. My initial velocity, right? That's just it. So check it out. My initial velocity is this green one, and I'm going to switch. I don't think I need to switch. Let's say, okay, the initial velocity, VI. And what's the height? Sorry, that's the height. What's the width? 10 in this situation, which is just a change in what? It is 10. You're absolutely right. And this axis represents the time. So this is just some change in time along the x-axis. So I'm going to use parentheses to make this as nice as I can. We'll say delta t. Now, I'm going to go back, and just so that mine looks a little bit nicer, you don't have to change yours, but I do want the colors to match a little bit, so I'm going to go ahead and change delta x sub bravo to yellow so we can keep stuff straight. Plus, how do we find the velocity, or sorry, the area of that triangle? I know it's 1/2 times base times height, so I'll start with the 1/2. What's the height of that triangle? So you said 5, right? Because you're looking at the graph. Love it. Cool with it. Gosh, well, the height is just this, yeah? This starting to ending velocities. Which, is there a better way to talk about the difference between where you start and where you end? Like some change in my velocity? What letter do we use to represent change? It's a Greek letter. It sounds weird when I word it that way. Delta, right? If we do this, if we say that's a change in velocity, because we can't just use VF because my whole triangle isn't 10 tall. It has to be between here and here is my height. That's just delta V. And I'm still multiplying my height times 1/2, which I already have written down, times what's this? There's a bunch of answers. Time, or a change in time specifically, right? Okay. Now, looking at it, these things get ugly for a moment. Before we continue on, there's a lot going on here. The notation is a lot harder than what the actual numbers are telling us, but we're trying to make it general. If you want to see this worked out in our concrete example, check it out. This works so nicely. It doesn't have to get any harder just because we're using this generalized stuff. If we looked at the triangle or the delta x of alpha on the actual problem, what's the area of this? 5 high and 10 wide, that's 50. Now that'd be meters because it'd be meters per second times seconds. Plus delta x, or the displacement in Bravo, is just the area here, which is 1/2 times 5 times 10 again. Can I just say 1/2 of 50? Can you tell me what the displacement is for this total object? It's 75 meters. And I can already see that. Doing it here, my hope is that you look at it and go, okay, that's really not bad at all. This, also really not bad at all, but the notation feels like it just makes it so much worse. If you can do this, you can do this as well. It just takes practice to get comfortable with the notation. All right. Questions before we keep rolling with this? Okay. Now, this equation winds up being pretty handy if we want to deal with it. I'm going to make a big comment here, and we'll find time for a brain break at some point today because there's a lot of stuff, just so you guys are aware. The statement that I want to make, and it's just going to be a little arrow. This formula works. This formula works if we know a bunch of stuff. Now, specifically, we're just going to pick all that information out. This formula that we just wrote, weird. This formula that we just wrote down only works if we know a few different things. Now, real quickly before we talk about this, what did we say we were going to use all this information to solve for? If we have time and velocity, what can we find? So displacement for sure, but I definitely know position, the final position, because we're going to be able to work through it. Where in here would x sub f be hiding inside this ugly formula? So I never wrote x sub f, right? But it's in there. If I expanded everything out with all the deltas, which part of this contains my x sub f? Is it going to happen in delta t? That's only going to have tf and ti, right? Is it going to happen in delta v? Well, that's just vf and vi, right? What about in here? Delta x contains what? Final xf and xi, right? So it's stuck inside here. Now, this formula only works if we know vi and vf. So I'm going to say vi, vf, and t. And specifically delta t. Now, we want this to help us streamline or to make our work more efficient. You could just remember and write this one down, whether you remember it or not is irrelevant to me, and you could expand it and solve it over and over and over every single time, but I don't think that's the best use of our time. Instead, if we can use this to get everything that we might need out of it, so that we have like 3 easy formulas that we're going to be able to solve for whatever we might need, this is going to work really nicely. So let's streamline it by doing the following. Let's expand and get quote-unquote nice equations. Sean, if you need to go get a drink, feel free. As we're looking for these nice quote-unquote equations, what we're after is just being able to make sense of what's going on. Specifically, delta x, how would you calculate out delta x? All right, I heard whispers. Get loud, get proud. If you're wrong, it's okay. I don't have my calculator there. All right, so we're going to get loud and proud here. Let's see. We have number... Fern. What's delta x expand to? Good. I agree. xf minus xi. And I'm not going to change colors because it's going to get absolutely messy if I try to keep that straight, if that's cool with you guys. Equals. Now, this delta v, or sorry, vi is just my initial velocity. I'm going to take a shot in the dark here. How many of you guys write your vector little arrow above it every time? I'm going to quit as well then, if that's cool with you. As long as we realize that vector, or that velocity is a vector and you have to be able to see the direction, we can make it look a little nicer without it. Okay. Cool. What's delta t? Oh, yeah, right, sorry. Number Angel. Love it. TF minus TI plus 1/2. And this is going to look ugly for a second, but I promise it'll work out here. Delta V, our natural urge is to do VF minus VI, right? Now, I want us to think about something else for just one moment, though. How do you define acceleration? And I know this is going to seem like totally off the wall, but I promise it'll relate back in. What is acceleration defined as? You may have to check back in your notes, but it's this change in something over a change in something. So I think, Rafa, I agree with that. Delta V over delta T. Everybody on board with that part? Man. Now, all of a sudden, we start the ability to substitute some stuff in. And if you were doing this on your own, just for the record, you may not feel like you're going in a specific direction. But I'm obviously going to push us down the right path that's going to make this spit out nicely. Could you solve this for delta V by multiplying each side by something? So yeah, let's multiply each side by delta t, and I could say that delta v is written like this as well. Everybody agree that that's a true statement? Now, whether or not you would notice this on your own, again, is a different story, but let's use this fact. Instead of this delta v, I'm going to go ahead and write out that this is just acceleration times delta t, and then I still have to multiply by this delta t. Now, as I look at my work, there's one thing that bugs me just about the way I've decided to write stuff. Notice I expanded delta t in one of them, but not the others, purely on accident. There's no rhyme or reason to why I did that. I'll either expand them all or I'll condense them all back down just to make stuff look a little bit nicer. Okay. Now, going through this, I think we have a nice formula about ready to show up. I'm going to make one more comment that just to be nice. Typically, what is our initial time? If you were to start timing something, what's your initial time at? Anybody start timing stuff at 4.3 seconds? That'd be weird. 0. If this happens and t sub I is typically 0, what happens with this t sub I and the t sub I sitting in there? They're just gone, right? We don't even have to subtract anything, which means I would like to suggest the following. Since that is normally the case, let's just let t equal delta t to simplify our notation as much as possible. If we start at 0, delta t is just my final time, and we'll just call it t. Now, in solving this, check it out. I'm going to make this so much nicer. We have x sub f minus x sub I is equal to, and we're just going to start simplifying. This is vi times, if we just let that equal 0 for initial time, instead of writing delta t or tf minus ti, what did we say just now we're just going to write? So I don't even need delta t, right? If we always make it 0, can I just call it t? So check out how nice this formula all of a sudden becomes as long as we get these nice things going on. Vi times t plus 1 half a, and this would just be t times t. Give me a simpler version of that. T squared. And one more step, and we're going to write 3 equations that wind up being equivalent, that wind up the same thing. We started out this whole problem talking about these areas and everything, trying to find a nice formula for final position. Can you solve this for a nice formula for final position? All I have to do is add what to each side? Initial position. And this is going to feel different than the math world. I'm going to put this x sub I first. Initial position plus initial velocity times time plus 1 half a t squared. We're going to take a 30-second break or so, and I'm going to say go check your phone, because whoever keeps dinging, I want you to make sure your phones are on silent or vibrate. Cool. Here's what I've not typically done before. From this equation, you can solve this for a variety of stuff, right? We have it right now solved for x sub f. Could you arrange this to solve for v sub I? Now, here's where I'm just going to have to trust you guys, because we can do it either way. This equation you could solve for x sub f, or x sub I, or v sub I, or a, or t, but it'd be a little bit more challenging. Do you want me to rearrange all these right now, or can we just say there's algebra that can solve for any of these? The second one. Okay. If you want me to help you with this, feel free to stop by. This can be rearranged to solve for anything. So I'm going to put a big star next to this guy. This is going to be an important formula. Okay. I want us to get one more, because this formula works really, really well if we know a bunch of stuff, right? It works well if we know time and initial position and acceleration and initial velocity. But you have to have all of that. Is it possible that sometimes your daily lives get a little busy and maybe you just don't have the time? So let's see what happens with this equation if we don't have time given then. I was proud of that joke when I thought about it yesterday, just for the record. I've been thinking about how I was going to work it in, and it felt right. Okay, realistically, we are going to do exactly that, but I want to do the following. First, I'm going to copy that so we don't lose it, because we will reference it again. Copy. Cool. Then all the way up here, we are going to knock out an alternate equation. From this first one, and I'll put this up above over here so that we still have it. I'm just going to let that one come along for the ride. We want an alternate equation. Now, specifically, that equation that we just worked out, that xf equals xi vit 1 half at squared, nonsense. It's not nonsense, that's a poor choice of words. Beauty. That works really well to solve for our final position. However, we don't always just want to find that. Other pieces that we might want, in this particular example we're going to see, is what if we want to solve this for v sub f? I don't know about you guys, but anywhere in that equation do you see final velocity show up? Never. So there's an issue that we have if we are ever after this. I'm going to preface this by saying, what if we had, and we're going to jump in with, let's say, VI, which, what's VI again? We'll do number, Kalisha, what does V sub I represent? Something about velocity, and is this initial or final? Good. If we had initial velocity, acceleration, initial position, but no time. All right. We are going to make a few little hand wavy things happen real quick. The other day, and I need you to check your notes. Again, it feels hand wavy, but I'm going to make sure that we take every step in a very specific way. You can find final velocity if you know acceleration and time, I think. Check your notes. We had a few important equations, probably from yesterday is my guess. or last class is my guess. Something with acceleration. You found it already? It's VI plus AT. Everybody on board? You may not have remembered it, but that's okay because you never have to remember formula for me. We're going to make a nice formula list together prior to any quiz or exam. You have that formula written somewhere. Now, my goal in this whole example that we're talking about is we're trying to find an equation without which value? Without time. So our whole goal right now, so it doesn't feel like magic, I want to get rid of this and I want to get rid of this. That's the only thing that I'm after right now. If I can write that equation without those, maybe, just maybe we can do it in such a way that we get VF. Can we solve this for t? Just this one. I would subtract VI. And then we're one step away from doing what? Or to solve it? Divide by acceleration. Okay. Again, the hand wavy part of this, these substitutions may not feel like supernatural if you were doing this on your own. That's okay. People spend a lot of time and a lot of thought into putting these equations together. We're just going to make sure that we can see how they did it without the recognition of, oh, how'd they come up with this? They were good at it. That's the real answer. All right. We now have this value. Let's see what happens to this equation if we try to change it. So plugging this in, let's see what we get. We would have x sub f equals still x sub I plus vi. What do we say we're going to use for t instead? Something to write t with only final and initial velocities and such. It's this guy, right? Vf minus vi over a. Okay, lovely. Plus 1/2 times acceleration times time. But again, I want an equation without any time. Vf minus vi over a. All right. How mathy do you want me to make you get compared to how mathy we get? So here's my first challenge. I want you guys, this is pushing on the border probably of your algebraic abilities right now. What are we trying to solve for? We're trying to solve for final velocity. Let's do that. Together, or do you want to try it alone first with your neighbors? Alone? Cool. All right. You are solving for V sub f. I'm going to give you a couple minutes. This sounds like I'm throwing like some pretty hard shade, and maybe I am. Let me know when you're ready to do it together. I hope somebody proves me wrong. Cool. Give you a couple minutes. Solve this for V sub f. This last one right here is squared. That's my bad. Now, that problem seems a little harder, or not. I don't know. We'll see. Give it a go. Solve for V sub f. This is easily the heaviest lifting that I'm going to make you guys do for a while in here. Like, once we get the formula, it's going to be easy to deal with. But it's kind of gross here. I don't care necessarily the order that we operate in. Where would you guys start out of curiosity? Where did you start? Trying to, anyway. What did you do first, number? Bea. What did you try to do? What's your first thought when you look at this and trying to solve it? You multiplied here? You multiplied this one, so you tried to do this? So time out. If you tried to do this, love the idea. Can you tell me why it's wrong, though? Why can't this a and this a divide out? The square. PEMDAS says we have to do the exponents first. So looking at this, I'm going to try to show like every possible step. I'm going to do 2 and 1 though, but I'll draw them out. First one, what happens when you multiply this by this? Starts with a D and ends with distribute. Okay, cool. So we'll distribute those, and then this thing also winds up squaring itself. So I will have some scratch work over here. We would have VF minus VI over A times itself, right? Now, I'm confident that everybody in here has the algebraic ability to do these, but you may not have the recollection and remember how all these things work, which is totally okay. Like, that's fine. Let's do both of those steps in this one. So we obtain x sub f equals x sub I plus, and it's going to get ugly, but I think that this is just vi vf minus, what else spits out in the numerator here? Vi squared, and that's still all over what? A plus 1/2, and we still have this lovely A showing up here, and then I will write this in parentheses. Let's just do some work here. Foiling with fractions looks like it's going to be ugly, but it's really just the exact same way, because fractions go numerator to numerator when you're multiplying, and denominator to denominator. Nothing crazy happens. What's VF times VF? So we get VF squared. What's VF times negative VI? And it's negative, right? Negative VI VF. So I'll write it out here just so you can see the scratch work. Minus VI VF. What about this one? Negative VI times VF. Same thing. And then finally plus VI squared, and all that would be divided by what? A. So it's ugly, I think, but let's deal with it. I can clean these up. Negative VI VF, or minus VI VF minus VI VF is just minus 2 VI VF plus VI squared, and all of that now is over what again? And I had a typo. I said it, but I didn't write it. A squared, because we did A times A. All right. Big step there. Before we move on, questions about that big step? Okay. Now, we're trying to solve for what? Final velocity. All right. So what would you like to do? Bea, I'm going to come back to you because I liked your first idea. It was just a little bit early. You did something with this A right off the bat. It didn't work because you had to do the parentheses, but now there's no square in here. Not this whole thing's not being squared. Am I allowed to do that now? Okay, that's a good first step. Beyond this, if you want to rewrite it, you can. I'm not going to make you, but I will, because it's going to look a little bit simpler each time. So this maybe still looks kind of ugly, but that's okay. Over A plus 1/2 and gross VF squared minus 2 VIF, VIVF, I'm sorry, plus VI squared all over A again. All right. Blah. Who loves having fractions? Okay, so I get that. What is in the denominator here on any part of this? A, and there's one more that's kind of hiding in there. 2. How do you undo a fraction? So you multiply by whatever you're dividing by, right? Now I'm going to do two things. To make it a little bit nicer, can I subtract x sub I first? If I subtract this, xf minus x sub I, and I know it might feel like we're going backward, but let's just think. It's almost like that piece is just gone. To clear a divide by 2a, I could just multiply both sides by what? And we'll write it out. I'll give this a second. If I do this, and we'll take little tiny steps, I'm cool with that. VI VF minus VI squared all over A. And I'm going to write this one a little bit nicer. Plus VF squared minus 2 VI VF plus VI squared. And instead I do it all over 2A. Just so it looks a little bit easier mathematically. What should I multiply each side by to bust my biggest fraction? By 2a, right? Now, notice, when we say multiply each side, we literally mean multiply each entire side. This whole side gets a 2a, and this whole side gets a 2a. All right. On the left, if you want to, and I typically do, but I call this xf minus xi delta x. Would you like me to replace it with delta x or just keep it as it is? The option is I can keep writing this or I can just write delta x instead. You would change it to delta x? Okay, I'll do that too. So we'll keep kicking. The left side, I get 2a times delta x equals, and then let's think about this. If I distribute here, what divides out? Just the a. And what is still there then? The 2, right? So if we take little steps, the a is gone, and we're still multiplying by 2. This is what I'm left with. Plus, what happens, what divides out when I do this one? The 2a, and I'm left with just this lovely expression. We are just taking little steps to try to simplify it. Whether I or you would show this much work normally, I don't know. But I think it's good just as an algebra review because this is heavier algebra than we've done in pre-calc so far. All right. Now we're just going to keep working through and see if anything naturally just wants to happen. Gut feeling, who haven't I called on? Mickey, we made eye contact. Anything left that is like obvious that you think we should do with this before we start trying to rearrange? Distribute. I assume that's a 2. Okay, so let's distribute this 2 to these two guys. We get 2a delta x equals 2 vi vf minus 2 vi squared plus vf squared minus 2 vi vf plus vi squared. Lots of writing for what's going to boil out to be super nice here in about 2 minutes maximum. What is unbelievably nice about the right side, Nick? So look at it. We're trying to, if you had this in front of you, your goal should be at this point to hope for any like terms. Do you see any? We have a positive 2 VIVF and a what? Hey, they gone. I also see a negative 2 VI squared and a plus 1 VI squared. Do those combine? If I had negative 2x squared and 1x squared, can you put those together? Yeah, let's just subtract 1x squared, right? So I think we're almost there now. 2a delta x is equal to, we have a positive VF squared from right here, and then negative 2 plus 1 of the VI squareds is just a plus VI squared. And all of a sudden, we are one little step away. And this one, because of all this work, we are going to go ahead and write the equivalent versions of it. But I want you to notice something. This may feel like something you've done before. Anybody ever seen those letters? QED? Quadirat demonstrandum. What's your favorite part about geometry? Really, it's probably your least favorite part of geometry. What does everybody walk into geometry afraid of? Because you all hear how bad it is. Proof. We just proved this formula is what we just did. This is an algebra proof, but we just did a proof. Now, as we go through, here's our big takeaway. I'm going to write 3 versions of this. There are incredible uses for this. One last comment, and this is going to be the very last thing. There's no homework today. Tomorrow will just be example problems with these. Cool. The last big comment. Given. So let me rechange that. I'm sorry. If we have any 4 values of, and we're just going to have a list, and let's just see what we need. For this equation, there's only 4 unknown things. Or there's actually 5, but we'll talk about it. What's one of the unknown variables in this equation that we just found? A, acceleration. If you have 4 of the following 5, or 4 out of the 5, what acceleration? What's another one? So we knocked out the A in there. Cool. Anything else that has unknown values in there? Delta X, which I'm going to split that one up. XI or XF. Other unknown values. We got that one knocked out. Initial velocity or final velocity. If you know any 4 of those 5, this can be solved. And I don't know if this is short or not. I'm going to say this is solvable in hopes that I've saved time. Now, these equations, first and foremost, this equation. Do I really expect you personally to be able to derive this on your own right now if I asked you to? Definitely not. That is not the whole point here, but I do think it's nice to see that motivation from the mathematics as we work through these things. We get the following. I have 3 versions of this prepared that we're going to use. 3 equivalent versions. The first of these is if you want final velocity, which is what we're after, you just subtract VI squared from each side. So I'm going to expand out my delta X while I do these. It is up to you if you want to. But I think that final velocity is just a square of your initial velocity plus twice the acceleration times your displacement. This is one version of that formula that says, look, if you give me initial velocity, acceleration, and positions, we don't care about the time. Doesn't matter how much time has passed. We know that it's just implicitly in here. Now, alternatively, other places that you might rearrange this. You might instead solve for x sub f, which if I'm thinking about this, I simply subtract vi squared, divide by 2a, and add xi. I don't mind if you didn't follow that, but when we look at this, it means we would get a fraction, vf squared minus vi squared, all divided by 2a, and we would simply add x sub I afterward. So we can solve for velocity, we can solve for position. We will see a lovely equation at the start of class tomorrow, the last one, for how you would solve for acceleration. All right, cool cats. That was a big day. I thought we'd have time for brain break. We didn't. Appreciate ya. Later, Raiders.